Good morning to all. In today's session, we are going to discuss the last two systems of the series of systems in the first unit. In the previous sessions, we already discussed six kinds of systems. But now here, as a pair, the last two systems can be considered as a pair. Now, we are going to discuss this pair of systems in this session. Let us start. Now, in today's class, we are going to start with discrete or continuous time signals or systems and discrete time systems. Now, here one more point. Continuous time systems and discrete time systems. Actually, these are signals. You can be considered as vice versa. Okay, let us start. So, in this continuation of this series of systems, now today's topic is continuous time signals and discrete time signals, or just you can make it as continuous time systems or discrete time systems, like that only. So, now just here we are going to discuss the first one is called regarding continuous. The second one is discrete. Continuous time signals and discrete time signals. So, in the beginning of this first unit, we already segregated what continuous time signals are and what discrete time signals are. So, all these signals should be worked out on a particular system. So, now just you can use the word system in place of signals too. So, now just here we are going to make it as continuous time signals or discrete time signals also. Now, just look at a continuous time signal always denoted by small t, where time is an independent variable. It depends upon continuous time. It depends upon discrete time, small n. So, here the signal is modeled as x of t. Here the signal is modeled as x of n. Here, for example, the width of the signal is from, the width of the signal belongs to, for example, 1 to 4. It always considers not only 1, 2, 3, 4, but also considers all the points between 1 and 2. And all the points between 2 and 3. Similarly, all the points between 3 and 4. This is the correct impact of this continuous time signal. That means what? That's why we are going to represent a continuous time signal in the form of a closed interval, for example, 1 to 4, like that. So, it not only considers the integers 1, 2, 3, 4, but also considers all the points between 1 and 2, 3, 2 and 3, 3 and 4, like that. Now, here, for example, here the sequence, here we don't use closed interval, we use the sequence of integers 1, 2, 3, 4 only. Just look at. So, the representation here is curl brace. Sorry, it is square brace. Here it is a curl brace. Now, just look at. That means what? Here it considers 1, 2, 3, 4 only. Considers 1, 2, 3, 4 only, but any points between them it doesn't consider. Any points between 2 and 3 doesn't consider. Any points between 3 and 4 it doesn't consider. That is the meaning of discrete time signal and continuous time signal. Now, third difference is that it is used, if you take any graph sketch like this, the graph can be, for example, like this. This is t. Here we have to make it x of t. Here this is 0, for example, 1, 2, 3, 4. Amplitude is, for example, 2. So the graph will be represented like this. Or you can make it, for example, 0. For example, 0, 0, 1, 2, 3, 4, like that. So what is the width of the signal? Here the width of the signal is from 0 to 4. Now just look at this part. This part we are considering as the signal, that is x of t. Here 2 is amplitude. This is the width. Now the same can be represented here as, look at, this is the graph. Here this is n, this is x of n. Here x of n. Here the numbers are 0, 1, 2, 3, 4. The same can be amplitude too. So here now just look at, this is the way of representing continuous and discrete time signals. Continuous time signal and discrete time signal. One more point. In continuous time signals, we are using only to calculate power and energy in a continuous time signal. We are using integration. In discrete signals, we use summation. Here is summation. So wherever we use the symbol, summation means the summation represents discrete. Wherever we use the symbolic representation, integration, this symbol representation is for continuous time signals. That is for discrete time signals. Next one. In this one, in continuous time signals, for example, just look at sinusoidal curve or waveforms. Sinusoidal curve, waveforms. All these are examples of these continuous time signals. Sinusoidal signal means what? Sine signal. It varies between, +1 to -1. So just, it goes like this. This is a continuous curve. Example of continuous curve. So all continuous curves, waveforms, electronic, all these things come under the category of this continuous time signals. Here discrete means what? Here digital signals, symbolic representations. For example, just look at waveform. All these are in the digitalization. In the digitalization we use. In the digitalization. So in this format, we use all discrete curves. Discrete digitalization. This is one more important differentiation between these two. Next one. Actually, in continuous curves, what is the advantage of continuous curves actually? For example, just look at, if an analog curve is there. Now one more point, the continuous time signals. Now just we use for this another word that is called analog. Analog is the electronic terminology for continuous time signals. Analogous, like that. If you go for any analog systems, the next topic is analog systems and discrete system, digital systems. So here in the continuous time, for example, suppose a sinusoidal curve is like this, or you take any other format, any other wave you can take it. All these continuous waves, they occupy less space. all continuous signals, they occupy less space, but digital signals, they occupy more space. That is important. They occupy more space. For practical applications, continuous signals are not that much efficient. Efficient, but not that much. Whenever we compare with digital signals, continuous time signals are not that much efficient. That is one more point. One more point. Continuous time signals, they cannot travel for long unless through cables. Understanding? But digital time signals, they can travel any longer places. That is because of those one of the reasons we are giving that efficient factor to the digital time signals. So this is continuous time signals. Now, this is for the continuous time signals. So here, for digitalization. In the digital signals, these signals are more efficient. These signals are more efficient than continuous time signals. More efficient than continuous time signals. One more point. These signals occupy more space, but continuous signals occupy less space. Digital signals occupy more space. Now, for modeling, we use in continuous time signals, for modeling, we use ordinary differential equations. Ordinary differential equations. Actually, for modeling this one, discrete transformations we use. Discrete. In some of the cases, actually very rare, difference equations we use there also. Differential equations are different, difference equations are different. So these are the different kinds of comparisons between continuous time signals and discrete time signals. Actually, we already given the required stuff in the beginning of the first class, discrete time signals and discrete time signals. So whenever there is a word regarding signal, there is a concept of signal. Students have to remember that for continuous time signals, this is for discrete time signal. Discrete time signals. So on these two signals, all and whatever the properties are there existing on signals, all properties are applying all these two kinds of signals. That means time shifting, time scaling, time reversal, all these properties are applicable to these two kinds of signals. So this is the end of this topic. The next topic we are going to discuss analogous systems and digital systems. Analogous systems and digital systems. Thank you.